I wanted to go over this worksheet with you. I felt like this is probably a little harder than some of the ones you've been asked to do. I wanted to take you through the very beginning of it. As you can see, if I go back, let me go back. So this is what my class work stream looks like. So I believe if you click there, then you have to open with Cami, which just allows you to have the editing tools over here on the side. So over here's your toolbar. This right here is just my recording tools. So I had these pulled out. You can toggle them back. So I'm going to open them up so they don't interfere with my recording tools. So at this point, these are some examples here. So if I opened up this, it would take you to a different screen where you could read about osmosis and CK12. And it talks about in a solution, you have the solute. So we used salt versus the solvent, which would be water. And the mixture of a solute and a solvent is called a solution. We kind of talked about when we talked about mixtures and solutions and colloids and so forth. And they're going to discuss hypertonic, hypotonic, isotonic. So if you get confused, you can go to this worksheet because you have access to it. And if you open up the CK12, it goes over these definitions with you. Hypertonic, comparing two solutions of unequal solute concentration. The solution with the higher solute concentration is hypertonic. So when we talk about hypertonic, hypotonic, isotonic, it's with respect to the amount of solute. We're not comparing water yet. We're comparing solute. So hypotonic means that one of the two solutions has less solute than the other. And iso remains the same, like an isosceles triangle. It's a triangle with all three sides the same length. Iso means the same. So if you're comparing two concentrations, they will have the same amount of solute. Okay. And here they're talking about the cells. And I think I've talked about this before. We kind of gone over this before, maybe. Here, if the solution that these cells are sitting in is hypertonic, that means it has more solute than the solute inside the cells. So this would be like more solute out here. Let's say this is 80% solute or 60% solute, and this is 40. If this is 60, that means that the water content's 40. If this is 40, the water content's 60. So the water moves from higher to lower. So since the cells had more water than the outside solution, the water left the cells and they started to plasmolyze or shrivel. Here, with an isotonic solution, there's the same amount of solute floating out here in the solution as what's the amount of solute concentration that makes up the cell. So the water can move into and out of the cell, but there's not an overall net influx of water, or there's not a net release of water from those cells. So this is isotonic. Here, these cells have more solute. There's more solute in the cells than in the fluid. So if there's more solute here, that means they have less water than the fluid. So the water rushes into the cell. And this, they're calling this the water pushing on the sides of the cell is the turgor pressure. You heard me mention that in the video about the osmosis. Okay, so this is just plant cells and a lot of water. They're very filled. They're exerting a lot of turgor pressure. All right, so we kind of went over part of this already. All right, So going back here to the CAMI export, in a salt water, let's see. So imagine you have a cup that has 100 milliliters of water and you add 15 grams of table salt or table sugar to the water. The sugar dissolves and the mixture that is now in the cup is made up of a solute, the sugar, that is dissolved in the solvent. The mixture of a solute and a solvent is called a solution. So the sugar is the solute, the water is the solvent. So in a saltwater mixture, the salt is the solute and the water is the, that's kind of being a little weird. I need to get a text box going there. The water is the solvent, okay? And the saltwater mixture is also called a solution. Okay. So here, I originally, when I put this worksheet out, we would have been doing this in class and I would have had you draw the images, but I know it's a bit much being at home trying to figure all this out, so I kind of drew some images for you. So this is a beaker, and I had to make it, it doesn't look like a beaker, I had to make a container that was big enough to put everything, all the writing and stuff in. So diagram a beaker containing a dialysis bed that contains a hypotonic solution, which means if it's hypotonic inside, it has less solute than the outside. So I put 20% in the bag and 40% out here. And then I filled in the water. If this is 20, then that has to be 80, has to be the water to equal 100. If this is 40% solute, then the other 60% of the solution has to be water. So your solute and water concentrations or solvents have to equal 100. Okay. Now, water goes from a greater concentration to a lesser concentration, so it's going to move out of the bag. And the way I did that drawing was I just clicked on the paintbrush, and you can even pick your own color. I guess I should do blue since we're doing water. And the water's going to move out of the bag. So then I went over and put and opened up my text box. Oops, don't need a blue dot on the text box. Oh, this is being contrary. Okay, I'm going to go use my eraser. Oh, it left. Okay, I'm going to go up here and go to my text box. And you can open up a text box, and that's how I put the X there. Okay. All right. Will these solutions ever become isotonic to each other? And that answer is yes. Because eventually, if you have 80 here, 60 here, eventually enough water will flow out. And so there'll end up being a 70-70 split. The water can still move back and forth, but it does at an equal rate. So yes, they could become isotonic. No, that's wrong. They won't be isotonic because isotonic refers to the salt concentration. So they may not, unless it dissipates it. If that becomes 70, that becomes, I'm wrong. I don't want, let me back up. They can become isotonic because if this becomes 70, that becomes 70, then these are going to be equal to 30 and 30. So it will be okay because the water will spread out and dissipate it down in this concentration here. So sorry, I had a moment there. All right, so here, diagram a cell, and I left this one for you to fill in. Diagram a cell in a solution that is hypertonic. So when it says hypertonic, we ought to go ding, ding, ding. That means solute. So diagram a cell in a solution that is hypertonic compared to the cytoplasm of the cell. So if this is supposed to be hypertonic, I can pick out a number. Let's do 60%, 60% solute. Hypertonic means it has more solute. That means the solute out here has to be less than 60. Any number less than 60 will work. So I can put 40. Then I can come back over here and figure out my water amounts. This total here, they have to equal 100. So if that's 60, that means this is going to be 40. If this is 40, has to equal 100 out here, that becomes 60, okay? Now, which way is the water going to move? Okay, so there's more water out here than there is in here. So I'm going to come over here and click on my drawings. See if I can get a marker here. So water goes from higher to lower, so it should flow into the cell. Now, if that water, if the, there we go, there it popped up. So if the water flows into the cell, that means this excess water is going to start creating pressure on the cell, which means it's going to expand the cell. So water will move. You can open up the text box and put X, or you can just do a check there. It's going to move into the cell. And the cell could eventually, if it's not a plant cell with cell walls, it could rupture. Okay. All right. If we go on, the next one, diagram a cell in a solution that's isotonic. Isotonic, usually your brain should go ding, ding, ding. Isotonic, same amount, iso means the same amount of solute. So I could put over here, which I would need my text box to do that. Expand that back out, click on text box. And when it opens up, I can put 45 there, which means I have to put 45 out here. These have to equal 100, so I have to put 55 there. And I need to put 55 here. Because it's equal amount of solute, equal amounts of water, if this membrane is permeable, then you will have the same amount of water moving into the cell as moves out. It will do so at the same rate. So basically, you could actually check here into the cell, out of the cell, and then I would put at the same rate. You could actually open up your own text box. You can click on text box and you can come over here and put water moves at same rate. You can actually type it in there, okay? So here, what kind of pressure builds up in plant cells when they are placed in hypotonic solutions? So hypotonic means that if they're placed in a hypotonic solution, that means that the plants are hypertonic, means they have more solute, less water. That means the water is going to move into the cells. And when water moves into the cells, there's a certain there's a word that we talk about, and I've mentioned it several times, it goes here. And this is kind of the same question right here. When pressure from water pushes against the inside of the cell wall, it is also called blank. All right, I'll let you figure those. They're basically the same way. I'll let you figure those out. And up here, I'm going to let you try to do this one on your own. So hopefully this will help you some.